Summary of Tableau 11, the fabulous limit laws. Part 2, the law of large numbers in continuous spaces, computation a la Monte Carlo. When we discovered the law of large numbers in the setting of the binomial, through the artifice of Chebyshev's inequality, it was already clear in the analysis that the mode of thinking was going to be wildly extensible. So the purpose of this lecture was to illustrate some of the features that emerge almost naturally from that kind of analysis. So to begin, we are going to have to extend and generalize the background we started with. So we first start with building up a background, a lexicon that we can utilize. I chose to specialize the presentation to a continuous setting just to illustrate how things segue smoothly from the discrete to the continuum. Though, as we've seen through the progress of this tableau, the analysis and the results extend much more widely. But accordingly, let's begin with a continuous setting. And the keys here are the continuous analogues of the ideas of expectation and variance. So to begin, consider a chance variable x, which is governed by a probability law conferred by a mass density function p of x. Recall, p of x connotes, in one dimension, a probability mass per unit length at the point x. The expectation of x now is defined as the continuous analog of a probabilistic center of mass. Of course, we'll call this mu, or write it more formally as E of x, and is now just a weighted integral of values weighted according to the mass density function. Now, the moment we go down to infinite domains, there are caveats we have to keep at the back of our mind. What I've written down on the screen is an improper integral with infinite limits, and we know from basic calculus that such integrals might occasionally fail to exist. So the caveat is if the expectation exists. Sadly, there are variables and there are densities for which the expectation does not exist. But in our setting, we have focused resolutely on variables where there is an expectation and indeed where there's an idea of variance as well. The variance connotes the probabilistic version of a moment of inertia. It captures the expected squared deviations of the values of a chance variable around its center, around its expectation mu. So we look at the deviation, square it, weight it according to the density function, and integrate out. Now, even if an expectation exists, there's a small possibility that the integral might diverge to plus infinity. Again, we focus resolutely on settings where we have an expectation and we have a variance. Now, with this in hand, the variance, as we have seen in the discrete cases, connotes an expected squared spread around a center. So the spread itself should be measured by the square root of the variance, or the standard deviation. This is actually captured beautifully by the elementary but wonderful inequality of Pafnoty-Chebyshev. So what does Chebyshev tell us? Chebyshev asks for the chance that a chance variable deviates from its expectation in absolute value by more than a designated amount. Let us say designated by the Greek letter tau. Chebyshev's inequality gives us a bound for this probability in terms of the variance. So the probability that x deviates from mu in absolute value by more than a deviation tau is bounded above by the ratio of the variance to the square of the deviation. Now, this is elementary. You should not run away with the idea that this is a very tight and very accurate inequality. The inequality is rather crude. Right? It's like taking a very blunt knife to a soft situation. You're going to get a crude cut. Its potency lies in the fact that it is so elegant and so simple. It requires so few constraints. And its largest impacts are seen when things are independent. And to capture this, we focus on settings where we have sums of variables. Additivity plays a large role right through the entire theory. And to begin, we observe that expectation is essentially a glorified sum, a limiting sum. Expectation is always additive. If we add independence to the mix, then we find remarkably that variance is also additive. So the expectation of a sum is the sum of expectations. The variance of a sum of independent summands is a sum of variances. This is the background we need, the tools which are going to fuel the res gestae, the key results to come. So what are the results that emerge from this kind of background? We immediately start with the idea of a random sample. Now, what is a random sample? Recall, a random sample constitutes independent selections from some underlying distribution. Let's say a generic chance variable is called x. It's got some probability law. And at this stage, the law could be continuous or it could be discrete. It makes little matter. We are going to draw, by independent sampling, a sequence x1, x2, x3, xn, and so forth, independently from the same law, the same distribution as a generic x. Let us say that this underlying distribution has got this common expectation mu and a common variance sigma squared. We promptly form the partial sums of this independent sample. So let S1 be x1, S2 is x1 plus x2, S3 is x1 plus x2 plus x3, and so forth, Sn representing the nth partial sum. Now observe that the variables in the sum are all independent copies of each other, statistically speaking. They're all drawn from the same distribution, and therefore they all have the same expectation and the same variance. Additivity of expectation immediately allows us to write down that the expectation of Sn is n times the common expectation mu. And because the summands are assumed to be independent, the variance of Sn is now n times the common variance sigma squared. It's a very potent and powerful observation. You see, because recall that spread is captured by the square root of the variance. The square root of the variance now behaves like the square root of n times sigma. Assuredly, the expectation is moving linearly in n, and for large n, it's going very far out. And assuredly, the spread around the center is increasing with the number of steps, but the spread is increasing much slower than the expectation actually is moving. Right? In 100 steps, the spread is only a factor of 10. In 10,000 steps, the spread is only a factor of 100. This potent observation, coupled with Chebyshev's inequality, gives us the law of large numbers. We call it the weak law of large numbers because, as I pointed out, there are stronger versions of this, which can say things about the entire sequence. But let us focus on the weak law of large numbers for the nonce. And what does this say? This tells us that the ratio of Sn to n, in other words, the sample mean, deviates from its expected value mu in absolute value by as small an amount as epsilon. What is epsilon? Your favorite tiny number, 10 to the minus 23.01, what you will. Fixed but arbitrary. The probability of such a deviation is bounded above by the ratio of the variance to n times epsilon squared. For any variance and any epsilon, however small, as n becomes larger and larger and larger, the bound on the right goes off to 0. And therefore, in short, the phenomenon we are describing here is that the sample mean, Sn over n, is increasingly concentrated around its center, its expectation, mu. You should pause to appreciate the wonder that's emerging here. We are dealing with a chance experiment. The variables x1, x2, x3 are fluctuating randomly, uncontrollably, and we're just adding. And somehow the sum of a bunch of randomly varying entities is behaving, properly normalized by n, as if it were a constant. It's as if all the uncertainty has been washed away, and we're getting an almost deterministic answer. This, as we've seen, has very potent and powerful consequences. We've seen a variety of applications, and let me list a smorgasbord of possibilities. It's a small set of the various things we can actually do. The earliest example we saw was that of poles, and this was what motivated our entrance into this canon. We see that we can estimate proportions of subpopulations in a large population very efficiently via a small sample. The same ideas, tweaked very slightly to create a double sample, can be utilized to check the efficacy of drugs, and this is at the heart of drug testing. We can use these models more generally to estimate expectations or means of underlying processes that are a priori unknown. For example, what is the mileage that you might expect in a new car? What is the rate of imperfection a semiconductor chip manufacturer might expect in their chips? What is the rate of production in a shift at a factory? All of these are presumably governed by chance laws for which we do not a priori, ahead of time, know the expectation. But if we observe these phenomena over a period of time and average them, then the law of large numbers is going to tell us that the sample mean is going to give us a very good estimate of the true underlying expectation. These ideas are utilized in quality testing, in the time to failure. How long does a computer have? What is its lifetime? How long will a light bulb last? How long before an aeroplane becomes unsafe? What is the life expectancy of a bridge? These are all questions of time to failure. If you think tongue-in-cheek of death as a failure, then we can utilize these ideas to design actuarial tables for life expectancy, for risk. All of these based upon the laws of large numbers. Going back in time, the earliest examples where people intuited a law of large numbers was in the theory of games. And of course, the law of large numbers now feeds in directly into a model, a theory of fair games. More subtle and sophisticated applications arise when we move into what appear to be deterministic settings, where we have to add a large number of quantities, we have to integrate known functions. And there, the complexity of the problem, as we've seen, can blow up very quickly with dimension to the point where it becomes fundamentally intractable because of a limitation in the resources available. Remarkably, in the middle of the 20th century, the discovery of Fermi, von Neumann, and Ulam shows us that we can replace deterministic computation by the strange and wonderful idea, a probabilistic computation, this ensemble suite of applications that we call Monte Carlo methods. Remarkable. These methods now have become a fundament in the 21st century. They pervade essentially every science. The laws of large numbers have applications in other areas. For example, in the design of optimal stock portfolios. How does one allocate resources in a diversified manner so as to maximize our returns? this is a very small set of the possible applications of the law of large numbers. What I hope to have done is to have stimulated your curiosity, to explore more widely. Now, with this under our belt, right, let us go back in our next tableau to the question of poles. The issue at hand there was the law of large numbers gives us large guarantees as to why poles work, why drug testing works. But we concluded Tableau 11, Part 1, with the observation that, encouraging as these results were, the crude application of Chebyshev's inequality gave us population or sample estimates which were still much too large for comfort. The question now is, can we revise downwards our requirements, our estimates, so that we can come up with estimates which are practically feasible and appealing? This investigation will take us in a beautiful new direction. And like a flower unfolding, we'll find the bell curve emerging from these ruins. This is going to be the subject of our next tableau.